The National Electrical Code, or NEC, specifies requirements for electrical installations to ensure safety. When dealing with three-phase power systems, one crucial aspect is managing unbalanced loads. An unbalanced load occurs when the current draw on each of the three phases is not equal. This imbalance can lead to excessive current in the neutral conductor, potentially causing overheating and damage to electrical equipment. According to the National Electrical Code, the maximum percentage of unbalanced load permitted is 20%. This 20% limit is based on the current in the largest phase conductor. In practical terms, this means that the current flowing through the neutral conductor should not exceed 20% of the current in the phase with the highest current draw. To illustrate this, consider a three-phase system where the currents in phases A, B, and C are 50 amps, 40 amps, and 30 amps respectively. The largest phase current is 50 amps. According to the NEC, the neutral current should not exceed 20% of this value. Therefore, the maximum allowable neutral current would be 20% of 50 amps, which equals 10 amps. If the actual neutral current exceeds 10 amps in this scenario, the system is considered to be operating with an excessive unbalanced load and corrective measures should be taken. Several factors can contribute to unbalanced loads in three-phase systems. Firstly, uneven distribution of single-phase loads across the three phases is a common cause. If one phase supplies significantly more single-phase loads than the other two phases, it creates an imbalance. Secondly, the operation of certain types of equipment, such as single-phase motors or welders, can also contribute to unbalanced loads. These devices draw current from only one or two phases, leading to unequal current distribution. Thirdly, faults or failures within the electrical system can also cause imbalances. For example, a short circuit on one phase can result in a significant increase in current on that phase, creating an imbalanced condition. It is important to note that unbalanced loads can have several negative consequences. Firstly, excessive neutral current can lead to overheating of the neutral conductor and associated components, such as transformers and panel boards. This overheating can damage the insulation and other materials, potentially causing electrical failures or fires. Secondly, unbalanced loads can reduce the efficiency of the electrical system. The increased neutral current results in higher line losses, meaning that more energy is wasted as heat. Thirdly, unbalanced loads can cause voltage imbalances, which can negatively affect the performance of sensitive electronic equipment. Voltage imbalances can lead to malfunctions, reduced lifespan, and even damage to electronic devices. To mitigate the risks associated with unbalanced loads, several strategies can be implemented. Firstly, careful planning and distribution of single-phase loads across the three phases is essential. This involves ensuring that the number and type of single-phase loads connected to each phase are as balanced as possible. Secondly, using three-phase equipment whenever possible can help to reduce imbalances. Three-phase motors, transformers, and other equipment draw current more evenly from all three phases, minimizing the neutral current. Thirdly, regularly monitoring the current in each phase and the neutral conductor can help to identify and address imbalances before they become problematic. This can be done using clamp-on ammeters or permanently installed monitoring devices. Fourthly, implementing automatic load balancing systems can help to maintain a balanced load even when individual loads change. These systems use electronic controls to automatically adjust the current draw on each phase to minimize the neutral current. In addition to the 20% limit on unbalanced loads, the NEC also specifies requirements for the sizing of the neutral conductor. The neutral conductor must be sized to carry the maximum possible neutral current. In many cases, the neutral conductor must be the same size as the phase conductors. However, in some cases, a smaller neutral conductor may be permitted, depending on the type of load and the specific requirements of the NEC. The NEC provides specific tables and guidelines for determining the appropriate size of the neutral conductor for different types of installations. These tables take into account factors such as the type of load, the voltage of the system, and the length of the conductors. It is important to consult these tables and follow the NEC guidelines to ensure that the neutral conductor is adequately sized to carry the expected neutral current. Another important consideration is the bonding and grounding of the electrical system. Proper bonding and grounding are essential for ensuring electrical safety and minimizing the risk of electric shock. The NEC specifies requirements for bonding all metal parts of the electrical system together and grounding them to a common grounding electrode. This creates a low impedance path for fault currents to flow back to the source, allowing protective devices, such as circuit breakers and fuses, to quickly interrupt the circuit and prevent electrical hazards. The NEC also addresses the issue of harmonic currents in electrical systems. Harmonic currents are non-sinusoidal currents that can be generated by certain types of electronic equipment, such as variable frequency drives and electronic ballasts. Harmonic currents can cause a variety of problems, including overheating of transformers and conductors, voltage distortion, and interference with communication equipment. The NEC provides guidelines for mitigating the effects of harmonic currents, such as using harmonic filters or oversized neutral conductors. The NEC is a comprehensive set of standards that covers all aspects of electrical installations. It is important for electricians, engineers, and other professionals involved in electrical work to be familiar with the NEC and to follow its requirements. Failure to comply with the NEC can result in serious consequences, including electrical hazards, property damage, and legal liability. In summary, the National Electrical Code limits the maximum unbalanced load to 20% of the current in the largest phase conductor. This limit is designed to prevent excessive neutral current, which can lead to overheating, damage to equipment, and reduce efficiency. To mitigate the risks associated with unbalanced loads, careful planning, proper load distribution, regular monitoring, and appropriate sizing of the neutral conductor are essential. Compliance with the NEC is crucial for ensuring electrical safety and preventing electrical hazards. It's also worth understanding how to calculate the percentage of unbalanced load in a three-phase system to ensure compliance and safety. Firstly, measure the current in each of the three phases. Use a clamp meter to measure the current flowing through each phase conductor. Label the readings as phase A current, phase B current, and phase C current. Secondly, calculate the average current. Add the current readings from all three phases together, and then divide the sum by 3 to find the average current. The formula is average current equals the sum of phase A current, phase B current, and phase C current divided by 3. Thirdly, determine the maximum deviation from the average. Find the phase with the current reading that deviates the most from the average current. Subtract the average current from this maximum phase current. The absolute value of this difference is the maximum deviation. Fourthly, calculate the percentage of unbalanced load. Divide the maximum deviation calculated in the previous step by the average current. Then multiply the result by 100 to express the imbalance as a percentage. The formula is percentage unbalanced load equals the maximum deviation divided by the average current multiplied by 100. Finally, compare the result with the NEC limit. Check if the calculated percentage of unbalanced load is within the limit specified by the National Electrical Code, which is typically 20%. If the calculated percentage exceeds this limit, it indicates an excessive unbalanced load condition that needs to be addressed. By following these steps, you can accurately calculate the percentage of unbalanced load in a three-phase system and determine if it complies with the NEC standards, ensuring the safety and efficiency of the electrical system. Addressing unbalanced loads is crucial for maintaining the health and longevity of electrical systems. Firstly, redistribute single-phase loads. Review the distribution of single-phase loads across the three phases. Move circuits to balance the loads as evenly as possible. Try to ensure that each phase carries a similar amount of current. Secondly, use three-phase equipment. Replace single-phase equipment with three-phase alternatives where feasible. Three-phase equipment distributes the load more evenly, reducing the potential for imbalance. Thirdly, monitor phase currents regularly. Implement a system for regularly monitoring the current in each phase. Use clamp-on ammeters or install permanent monitoring devices to track current levels. Fourthly, install harmonic filters. Consider installing harmonic filters to mitigate the effects of harmonic currents. Harmonic filters can reduce voltage distortion and prevent overheating of equipment. Fifthly, upgrade neutral conductors. If excessive neutral current is a persistent problem, consider upgrading the neutral conductor to a larger size. A larger neutral conductor can handle higher current loads without overheating. Sixthly, check connections. Inspect all electrical connections for tightness and corrosion. Loose or corroded connections can contribute to imbalances and increase resistance. Seventhly, use load balancing systems. Install automatic load balancing systems to maintain a balanced load. These systems automatically adjust the current drawn in each phase to minimize neutral current. Eighthly, conduct regular inspections. Perform routine electrical inspections to identify potential issues early. Regular inspections can help prevent imbalances from becoming severe. Ninthly, consult with an electrician. If you are unsure how to address unbalanced loads, consult with a qualified electrician. An electrician can assess the system and recommend appropriate solutions. Tenthly, document all changes. Keep a record of all changes made to the electrical system. Documentation helps track load distribution and identify potential issues. By following these measures, you can effectively address unbalanced loads and maintain a safe and efficient electrical system.